If we're dealing with a binomial experiment, we can also look at calculating what are referred to as the expected values, the outcomes that are likely to occur as a part of this experiment. We can calculate those expected variables as n, the number of trials, times p, the probability of success. And then we can calculate the standard distribution of a binomial distribution as the square root of n times p times q, where q is the probability of failure. We could also rewrite this as n times p times 1 minus p, since p and q are complements of one another. We can use these values to determine likely and unlikely outcomes for a given binomial experiment. In example 3, a given country has a lung cancer survival rate of 20.8%. The age standardized percentage of patients with lung cancer who survive for at least 5 years following their diagnosis. Assume 281 people who have recently been diagnosed with lung cancer are randomly selected from this country. Given a large enough population, selection without replacement can be considered independent trials, which again allows us to consider this a binomial experiment. We want to complete the following. Find the expected value for this binomial situation. The expected value, again, is n times p, where we have 281 trials, 281 people who are selected, times a probability of success of 0.208. That gives us an expected value of 58.448. Then we can calculate the standard deviation for this experiment, which would be n times p times q. So that would be the square root of 281 times 0.208 times 1 minus 0.208, which will be approximately 6.8037. In part C, then, we're asked how many people from this group would you expect to still be alive 5 years after their diagnosis? To determine that, we take our expected value of 58.448 and we both add and subtract the standard deviation. This will give us two different results, 51.6443 and 65.2517. Now we're talking about people. We can't have a fraction or a portion of a person. So that means we would expect between 52 and 65 people to still be alive 5 years after their diagnosis. Those would be the usual expected values based off the sample size and probability of success in this scenario. Then in part D, we're asked to provide an unlikely number of people from this group to still be alive 5 years after. That means anything outside that range of 52 to 65. So something like 50 would be an unusually low number. And a high number would be anything above 65, so something like 75 would be an unusually high number. Because again, what we're saying in part C is that we would expect between 52 and 65 people to still be alive 5 years after their diagnosis, based off the parameters that were given in this binomial experiment.